Okay, Assalamu alaikum wa rahmatullahi wa barakatuh. Bismillah ar-Rahman ar-Rahim. We will start from where we stopped in the first half, which is we were talking about the fact that the incidence matrix usually for big collections will be very sparse. Okay, so that's not good in terms of memory, of course, right? So if we have a collection that has billion of documents, that will not fit in memory. Okay, although the number of fonts might fit in some cases, but the entire matrix cannot actually easily fit. So it's not a good representation. Now the question is, what is a better representation? How can we do that more efficiently in terms of memory space? Any ideas? Did we see that in computer science before? Yes. Yes, so the typical solution here is to, instead of having the complete row for each term, okay, then we just have a list of documents in which that term appeared. Okay, now, so that will be a list. Instead of complete row in the matrix, it will be just a list. Okay, now, how can we present the documents, and how can we say that this is document number 10 and this is document number 15? So we have to give IDs to the documents. Okay, so we have to assign a unique ID for each document. In that case, it will not be just the number of columns, right? Because there will be no columns in this case. We have to say that this term or this word appeared in document number 7, 15, 25, and so on. Okay, so we will have something like this. For each word, instead of having complete row of zeros and ones, now we will not have zeros and ones, right? We don't need to, because whatever document that will appear in that list, it will be one. It has one, okay? Which means that this word appeared in that document. So we don't need to put any bits anymore, and we'll just have the list of document IDs. Okay, so that's much more efficient, right? Much more efficient. Why is that? Less, I know it's less space, but why? Why it's much more efficient? More efficient in terms of space. Much more efficient in terms of space. Yes? No, just the space now. The space of this data structure will be much less. Yes? Yes, yes. Yes, so in other words, we don't need to represent the zeros here. The zeros are implicit, right? We don't need to say that this document, this term didn't appear in that document. It's implicit. If it's not in the list, then it's not there. So we saved lots of zeros here, okay? Which was almost the entire matrix. If you remember 1 to 499, it's almost the entire matrix. But what did we lose when we do something like this? The ease of doing the operations as we did before, right? In earlier, when we did this evaluation of the Boolean expression, it was very easy because we do the operations on the rows. Now we don't have these rows, right? Right? We can reconstruct them if we want, but again, the rows will be very sparse. Okay, and you will have to if the number of documents in the collection is billion, so we have to have a matrix of 1 billion entry. Okay, almost all of them are zeros, so it will be inefficient. But that's what we lost. We'll have to address this. Okay, so there must be other efficient ways of processing such data structure for Boolean retrieval and for retrieval in general. Okay, because even for inshallah, when we see the other models, we will never use this matrix. So this matrix was just a concept that we introduced in Boolean retrieval. But from now on, forget about the incidence matrix. We will never be able to use it because it's very sparse. It's not usable. So we will always use such structure. We call such structure inverted index. So that's the first time we use the word index now, right? So inverted index. Why is it inverted index? Because usually we have a document that has terms, right? Here it's the opposite way. We have a term and we have the list of documents in which this term appeared, or this word appeared. That's why it's called inverted index. Okay? Now, some of the definitions, some of the very important definitions. Each entry in this list, so you can think of this as a linked list. Okay, for each term. Each element in this linked list, we call it posting. We call it posting. So each posting refers to one document with respect to that term. Okay? So the posting, for now, it has the document ID. And as you see here, these are the document IDs. And it can have also other information that we will, inshallah, mention over time. Now, the entire list is called, since one of them is called posting, the entire list is called postings list. So every term has how many postings? It depends. Every term has how many postings lists? One, only one. Okay, so it's just one list, and that list, the length of that list depends on how frequent the term is in the collection. If it appeared in so many documents, then this list will be very long. If it's not, then the list will not be that long. Yes? Maximum number of documents in which is what? Yeah, I understand your point, but I'm asking you which is what? Yes, exactly, which we call the collection size. We call the collection size. Okay, so the collection size is the number of documents in the collection. So the maximum length of that posting list is, of course, all the documents in the collection, right? Do we have this case? Do you think that we will ever have such case that one word appear in every document? But every document has I think every document has the. That's more logical, right? So that, yes. Every sound clip maybe has or audio, but not every document. But every document might have, most probably, will have the somewhere, if it's long document, of course. Some short documents might not have. But there appears a lot. It might, the posting list for the will be very long. Okay, but most of the words will not appear in many documents, so it will be okay. Now, one point to keep in mind, and we will justify it hopefully today, that the postings list is sorted by document ID. Just keep that in mind. Okay, and you will see that here. Okay, it is sorted by document ID. It's not just random order of documents, but it is sorted by document IDs. What happened to the guys here? Huh? Leave? Okay. Okay, so it's sorted by document ID, and we will talk about that, inshallah, later. Now, the other side, which is the list of terms, is called the dictionary of the index. Okay, it is called the dictionary. So that's just a definition, terminology here. Why is it called the dictionary? We know the word dictionary, right? What is the meaning of dictionary? It has a list of all words, right? So that's a list of all words in the collection. So that's the dictionary of the collection, actually. Okay? Yes, we still call them terms. We never change that. It's always terms. And the entire list of terms is called the dictionary, and also sometimes called the vocabulary of the are the same thing. Okay, vocabulary set or the dictionary. Okay, now let's talk about, let's stop a bit since we talked about inverted index and talk about the general process of building an index. Okay, and then we will get back to how we can use this index to do it Boolean retrieval. Yes. In the actual dictionary that we use, does it have repeated terms? Same thing here. It's just and of course with the index, okay, this side shouldn't have any repetition, right? Because that's every unique term and all the documents that in which this term appear. So the terms, of course, are unique. Yes. Now the construction of the index, it has generally 3 steps. The input for the first step is the documents that we want to index. Okay, so that's the collection. All documents that we want to index. So, for example, this is one of the documents that we saw in the TOEIC collection we used before. He likes to wink. He likes to drink. So that's one example of a document. Okay. Now, given the entire set of documents, we do a process called tokenization. Tokenization. Okay. What do we mean by tokenization? We convert the document into a stream of what we call tokens. So tokens are you can think of it at that point, are separate words, okay, as they appear in the document. So for this document that you see on the slide, it will give us back this stream. He likes to wink. He likes to drink. Now, what do you notice about the output here of that step?
No punctuation.
There is no punctuation. Okay, so and that's exactly why or how we do this tokenization. Okay, for English, for example, we look for, that's the easy way to do it. We look for spaces, white spaces with maybe tabs, and punctuations. We assume that these punctuations are the separators of the words. Okay? So we'll just stop at this and we'll just remove it. By the way, we'll talk about this step in the 4th lecture, inshallah, 4th week. But for now, just assume that they will be removed. Okay, so we'll have this list of terms. What else do you notice? Yes? There is what? Yes, very good. And that's why we call it tokens. At that stage, they are exactly as they appeared in the document. We didn't do any aggregation. Okay? So just the stream of words that were written in the document. Okay, how about capitalization at that point? They are still the same, right? So the words, the characters as they are. We didn't do anything. We just got the tokens separated by these punctuations and the white spaces. So this process is called tokenization because each of these units are called token, and the output as a whole is called token stream. Now the second step is called normalization. Okay, what do we do in normalization? We start to have what we call terms now. So they are no longer tokens, they are terms because we do some processing for each term. So what do you notice here? First, capitalization, everything is small. Okay? So that's one of the steps in normalization. What else? No what? Likes converted to like. So there is something happened here that makes likes to like. There is no to. So we call these words stop words. Okay, we'll talk about all of this step, inshallah, in week 4, which is about document representation of reprocessing. Okay, so this all of these steps are done in the normalization phase. So the output of that step is called terms. Okay, it will be a stream of terms. So first we have a document, then we have stream of tokens, then we have stream of terms now. Okay, and by the way, generally terms might not be natural words. Eventually, and they look words now. Okay, but when we talk about the details, you'll find that sometimes the resulting terms are no longer, some of them are no longer actual words in the dictionary. They might be parts of the words. Okay? So you can think of them as modified tokens. The last step is the actual indexing part, which will take that stream of terms and converted it into the data structure that we saw in the previous slide, which is called the inverted index. So that's just the overview of the process. Of course, we didn't say anything about the details, how is that done, but these are the steps. That's the pipeline of the index construction. Tokenization, normalization, then indexing. And of course, indexing has so many details. We have a separate lecture for how indexing is actually done efficiently. Okay, so the resulting outcome of this process is called now the inverted index. Any question about this? Okay. Now the first two steps are called pre-processing. The first two steps are called pre-processing. So this is pre-processing for the document, with the meaning that we are preparing the documents to be indexed. Okay, so pre-processing. Now we'll look further into this third part or third step, which is indexing. Okay, we'll go through a very simple algorithm to do indexing. Okay, now we'll assume that we have now a stream of terms. That's the input to the indexing part. Okay, so now we did all the pre-processing. We converted every document as a stream or bag of words or terms. Okay, we call it bag of words because if we said bag of terms, it will be really silly, but it's actually bag of terms. Okay. But we call it bag of words. Okay, now we assume that we have this this stream. We will, out of this stream, for every document, that's the step one in indexing now, we will get what we call term sequence. So we'll put, we have a sequence of term document ID. So we will repeat for every term the ID of the document in which that term appeared now, for every document. So let's say that we have two documents in this collection, document 1 and document 2. We process document 1 first. We put all of this is what up to this point. This is that terms stream out of the pre-processing. Okay, so you see, for example, there are words that are repeated. That's exactly the same order that appeared in the document, but actually we don't care about the order so far. But just as the output was, it was just the same order that appeared in the document. And then we add the second document, each word associated with the document ID. So we'll see that from here we have, this is the terms that appear in that document, and in front of each is 2 because that's the document ID for the second document. If we have third document, we have the terms for that document and so on. So all of them will be just in one array, one very big array. Okay? So this is a sequence of term document ID pairs. Each row is a pair of a term and document ID. Okay, with me so far? So that's straightforward, right? Okay. Now the second step, so this is the pre-processing part. Now, which is just an initial step of the indexing. Now, the second step, which is a core step in indexing is to sort this list, this array, by term. What do you mean by sorting by term? Sorry? Alphabetically, yes. Lexically, we call it lexically. Okay, we sort it alphabetically. Of course, we sort the rows, and every associated pair will be with that term. Okay, so if we do that for what we see here in the slide, we get this matrix back. Now, if you look at the column of the term, you will see that it is sorted alphabetically. Okay. What do you notice also on that in that matrix now or array? There are repetitions, of course. Okay, repetitions because some words appear more than once in the same document or in other documents, because you know now after sorting by term, all the entries of the same term, whether in the same document or in other documents, will be together, will be after each other. No, we didn't. Where is that? No, in normalization we didn't. Okay, we didn't. We get rid of, as an option, we get rid of stop words, but here we didn't. Okay, it's just an option. Okay, so we get this. Now, after we sort by term, as we said, for example, the word here for that document's capital appeared, not capital. Brutus. Okay, this is Shakespeare plays. Brutus appeared in document 1 and document 2. Okay, so when we sort by term, then we sort by document ID. So for each term, the entries will be sorted by document IDs. Okay, so we'll see here Brutus 1, Brutus 2. That means that Brutus appeared in document 1 and document 2 also, but we sort by document ID. Okay, is that step clear? Now, as I said, this is a core indexing step, sorting. We have to do that sorting. Now, what is remaining to get the inverted index? We have to go through it sequentially. Whenever we see the same term, what do? We add to the posting list. It's posting list. Okay, so we add to the posting list. Then when we get a new term, we add it to the dictionary and we start to collect for the new posting list. Okay, so going through this, that's the third step, which will create the dictionary and the postings. Okay, so we'll have the dictionary, and each term will point to the list, the corresponding list, which is the posting list. So for example, you see here Brutus, forget about this number for now. You see Brutus, and on the side of the posting list, you have 1, then 2. Do you remember when I told you that the posting lists have to be ordered, have to be sorted by document ID? Okay, that's done in step 2, right? When we sort by document ID for each term. Okay, so now it's very easy. Just by the same order that appeared in this matrix, we'll just convert. It's like we are converting this. If we look at Brutus, we converted this into this, right? Okay. And for example, this killed to this. What happens to killed? Here we had 2 entries, right? Here we have also 2 entries, but we got in here 1 only. Because it's same document. Remember, there is a posting for every document, not every occurrence. Okay? So if a term appeared in a document multiple times, there will be just 1 posting for that document for the posting list of that term. Okay? Type. Now, what is that number that is besides every term in the dictionary? How many? How many repetitions? How many postings? Which is, logically, what is the meaning of the logical meaning? The number of documents in which that term appeared. Okay? The number of documents in which that term appeared. We call this in IR, we call it document frequency. Okay? Might be confusing, but it's which is the number of, yes, which is the number of postings, because that's the number of documents in which that term appeared. So for example, Brutus appeared in 2 documents, so we have 2 here. Killed appeared in 1 document, although it appeared twice in that document, but document frequency is not about how many times it appeared in every document, it's about how many documents in which that term appeared. So killed has just 1 here. Okay? Questions? Yes? Yeah, forget about that. Assume that it's fixed somehow, that we will do capitalization or not. Ah, yes, all of this kind of work is done here. Of course, before sorting. Yes.
Doctor?
Remember, this column or this matrix is the output of is after the output of the normalization. Okay, so we are done with the normalization, then indexing starts. Yes, Muhammad?
Yeah, so just to confirm, that means the length of the linked list is going to be the frequency of the word, right?
It's called document frequency.
Yes.
Okay?
So it's essentially the length of the linked list, right?
Exactly, it's the length of the posting list.
Thank you very much.
Okay. Yes. It is, but it's a list. It's the size of the list. Any other questions? This is very important to understand. This is, it is very simple, okay? But it's very important to understand how the index, with this simple idea, of course, we will talk about other more complex algorithms of indexing later. But for now, I think it's very important to understand how this is done and what is the output in each step. Okay? Questions? So if I ask you to implement this, would that be hard? The steps are really straightforward, right? Okay. Okay, the document frequency, by the way, is called DF in short. Okay, document frequency, DF. So document frequency is a property of a term because it's just a number for every term in the dictionary, right? Does it belong to, or is it associated with a specific document? No, it's a specific term, okay? So the document frequency information is added here for a reason that we will discuss today, inshallah, to the dictionary site. Okay. Right. Now, how do we index efficiently? Of course, this is not very efficient. For example, we built this matrix as a whole for the entire collection, right? That's not scalable. If the collection is huge, this very first step will not fit in memory. Okay? Of course, it's more efficient than the matrix, the incidence matrix, but still this is not scalable. But it's very simple to start with as an idea to show you what is the index actually. Okay? Right. So later, inshallah, in the course, we'll see how we can do that more efficiently. Okay, now back to question? Question? Okay. Back to Boolean retrieval. Okay, we switched a bit the topic because we thought that the matrix is not efficient, right? And we had to find another way that is more efficient. Now we have another way, which is the inverted index. Now let's see how the inverted index can be used to do Boolean retrieval. We know how to use the matrix for Boolean retrieval, right? But now let's after replacing the matrix with the inverted index, how we can do it. Let's assume that we have a query like this, wink and, not dink, of course, it's drink, so that's a typo here. Okay, so wink and drink. And we want to get back the documents that match this query. Okay, just the end. How would we do that? Using the inverted index, of course. So here are the steps. So what do we actually know? What is given to us? Yeah, we have the inverted index, right? And we know that we have wink, we have drink, and we need to do something with them, right? So the first step should be retrieving the posting list of these two words, right? So we'll get from the index the posting list for wink and drink. Before we get into the details, let me ask you a question. This index generally, for very big collections, do you think that it should be completely in memory? And whenever we get a query, the whole index should be in memory? Of course not. Okay, so the index usually is mostly on disk, and maybe some parts of it in memory. Okay, but mostly on disk because that's huge. For web collections, it's really huge. Okay, so it cannot fit on even the disk of one machine. Okay, so that's why we will talk about, inshallah, scalable ways of indexing later in the course. Okay, but for now, just assume that everything will fit in memory, just for simplicity. Okay. Right. If everything now fits in memory, then we have in memory the posting list for all words, so we can just get from the index the posting list for these two words. So we'll get one for wink. Of course, there is a mismatch here, so it should be wink, not likes, and drink, not wink. Okay. So anyway, we will get the posting list for these two. So that's. So this is wink, and this is drink. Okay, so we'll get these two posting lists. Then what? What should we do? Remember that we need to do and. Why is it intersection? Yes, yes. So why is that the intersection of these two lists? Yes. So the documents that will satisfy this specific operation will appear in both posting lists. Okay. So what we actually aim for now is to get the documents that appear in both lists. This is a typical problem in computer science, I think, in data structures course or algorithms course back in the golden age 50 years ago. You studied something like this, right? When you have two lists and you want to get the intersection of them or merging them, if you remember, okay, very similar to what we called in data structures or algorithms courses, merge sort. You have two sorted lists and you want to merge them or get the intersection of them or get the union of them. Okay, so this is typical. So let's go through it quickly. What we will do, we'll start with. So we need to measure these two posting lists somehow. How? Here is how. We'll start with the beginning of the lists, okay, and we compare the numbers that we are pointing at. Are these numbers the same? Remember that we want to get the numbers that will be the same across the two lists, right? Because we are doing AND here. So 1 is not 2, right? So what should we do now? So it's not a match now. So there's no match till now. So what should we do? We should advance which one? The smaller. Okay? Because we should not advance the largest, right? If we advance the largest, 2 is gone. Okay? So we'll have to advance the smallest. So we'll advance the smallest. Now we have a match. Okay? Whenever these two numbers are the same, we got a match. So that means that this document satisfies the operation. So we should keep it in the output list. Okay, so that's one result. Now we got one result. What should we do now? Advance both. Okay, advance both. So advance both, we get 4 and 3. Advance 3, we get 5. Advance 4, we get 8. Advance 5, we get 8. Now we have another match. Okay, so now we add 8 to the result list. And so on. Okay, so we continue until we reach the end of one of them. Once we reach the end of one of them, what should we do? We should stop, right? Because we will not get any more intersections, right? So we'll stop here and declare that the result of this operation is 2 and 8. Okay? So this is very similar to the merge sort algorithm, or merging two sorted lists. Did you notice now why we need them sorted? What happens if these lists are not sorted? We have to sort them. Okay, but the sort has been done. Okay? Type. It has been done, right? Why don't we do it here? I mean, instead of doing it earlier, we just do it here. It will be the same, right? Why not? More efficient? Why? It's sorting there, sorting here. Very good. The sorting that we did was offline, was at indexing time. It's done offline. This one is done online. Why is that online? Because that's a query now. Okay, that's the query now. Now we are doing that after the user has issued the query. So that's very critical. We have to be very efficient here, very fast. Okay? So this has to be sorted. I think now you know why. Yes. Yes, but every query, if we didn't do it offline, we have to do it every query. No, terms will be covered by many queries, right? So we don't need to do that. Yes. Questions? Questions? Okay, now what is the complexity of that? What do you mean by complexity here? The time complexity, of course, right? What is the time complexity? Huh?
Of
Sorry? The length of the posting list. Of both. So if... Okay, type. I heard the smallest of them, and I heard both of them, right? What is the worst case?
is to traverse through the bigger list.
The bigger list. Okay, so I heard now a third answer. So there is the smallest list, there is the biggest list, or longest list, and both. Yeah, but to reach the end of the largest, I think smallest, we cannot do smallest, of course, right? Because we waited until we get, actually, it depends. So we cannot just say that it is the length of one of them. Because remember that we are actually pointing to every entry in both. It's not just one. Okay? So it's not just the smallest or the largest, but it seems like the sum of them, right? The worst case, I have to go through all of them. Time. Do you understand it? Okay. Now, what is the actual worst case? The worst case. No occurrence? What do you mean by no occurrence? Who said no occurrence? Yes. No occurrence of what? Okay, you mean no intersection. We don't care, right? Because we have we have to wait until we get to the end, right? But okay, so let me explain that a bit. What is the worst case in terms of the size of the lists? And we said that, so the complexity, I think we all now agree that if the size of the first list is x and the size of the second list is y, then what is the complexity, the time complexity? X plus y or x times y?
Plus y.
Okay, I heard plus from the speakers, and the speakers are much louder than you. Okay, why is it x times y? With everyone? But we are not doing it we are not taking one and going through all the others. We are always matching one by one here, okay? And we are going sequential over both. So it's x plus y. We will not actually go, okay, so just to understand it more, we will not point to one posting more than one time, right?
Doctor?
So it's the sum of both. Now, Muhammad, you have a question?
Yeah, I mean, this is what I'm curious about. Why do you keep saying, m plus n when it should be just n? Because we always care about the worst case scenario, which is
Yeah,
the
we didn't
longer
get
of
to
the.
that. Okay, so the worst case scenario is n plus m or x plus y if we use the x plus y. So that's the worst case in terms of given one query. Okay?
Yeah, but
Given one query, given one specific or set of posting lists, if we're talking about two here, then the worst case is to go through every entry in both. Okay? So if it's n and m, then it will be n plus m. Okay? Now,
yeah,
my question is, what is the worst case value of n and m?
2n.
No, yes?
Yeah, it's the size of the collection.
Sorry, Taiba, there's someone answering. Yes? Very good. 2 times the size of the collection. Why is that? Yes, so because the worst case length of any posting list is the size of the collection. Okay? So that's the worst case. That's the worst case. So it will be order of the size of the collection. But hopefully that will not appear a lot. That worst case will not appear a lot, except if I keep in the index and most of my queries has the so it will be catastrophic. But on average it won't be a problem. But the actual complexity is the size of the sum of the sizes of the posting lists. Any questions? Is that clear to everyone? Okay. Okay, and we said why is it crucial or very important that the postings are sorted by document ID. Okay, here's the pseudocode. I think this is in your textbook. We start by an empty answer. The P1 and P2 are the pointers. Okay, so we P1 and P2 are the pointers to the posting list. So initially they point to the first entry in the list. Okay, we will stop this loop when one of them is null, which means we get to the end of one of them. Okay, as we saw. If that's not the case, then we will check if the document ID of that pointer is matching. Then we add that to the answer list, and we advance both. Okay, and if not, then we advance only the smaller of them. And that's exactly what we did in the previous slide. Okay, any question about this pseudocode? Okay, good. We call this kind of process, before I say this, this process is called generally, okay, it's called query evaluation. Query evaluation, okay? This is the query evaluation process is a process by which we determine which documents we will retrieve back to the user. When we get the query, we do some work. Sometimes also it's called query processing. So query processing, query evaluation It's the work that we do to get back the documents to the user, to determine which documents we will get back to the user. Now, in query evaluation, there are many ways of doing it. One of them, which is popular, is called document at a time. Okay, document at a time. Why this process is called document at a time? Because it's like we are trying to get to make a decision for each document one at a time. We don't go term at a time. We don't go to the posting list of one term one by one. No, it's like we are actually accessing the columns in the matrix. Okay, but because we don't have the columns, we have to go through the postings. Okay, so that's why it's called document at a time. We are trying to align the documents so that we can make a decision for one document at a time. Okay, later we will know another method which is called term at a time. Okay, but this is called document at a time. So there is a way to actually go through one term one by one instead of going through the documents. Because we are trying to align the documents, we are trying to make, we are not keeping track of all the documents at once. No, we focus on one document at a time to get a score for it or to know whether we should retrieve for that query or not. Okay, now my question to you is, how can we modify this this code? Of course, this sort of code works for AND, right? For the intersection. But AND is not everything in Boolean, right? There is OR and there is not. Okay? So how can we modify this to do OR instead of AND? Would that be easy or not? Think first of what is the meaning of OR. And if I told you wink or drink, and now I have the two posting lists, yes, what is this?
We essentially just add them unless they're... No, we just add them regardless.
Huh? What? The union. Very good. Instead of the intersection, we need the union, right? Because we need any document in which any of these two terms appeared. It doesn't have to be both. Any of them. So all the documents that appear for the posting list of drink, plus all the documents that appear in wink, right?
I think the only challenge here is to make sure we don't have duplicates, no?
Oh, yes. So he is answering, I think, what you are saying. Can you repeat what you said? Okay. We don't need to compare. What do you think? Why we shouldn't repeat? Why? No, sorry. Why we don't need repeated documents? Of course, right? The user will be annoyed if you gave the user multiple results for the same document. Okay, so we care about, of course, removing the duplicates. Otherwise, we'll just add, concatenate these two lists together, and that's it. Okay, so we would have to get rid of the duplicates. How can we modify this to do that efficiently? Yes. So tell me which line number? 8 and 9. What should we do? Yeah, we shouldn't modify anything above 8. Sorry, Muhammad. Wathiq is answering.
No.
No. Okay, so we'll not change anything here. Okay. So. Here, so we add both. Yani we shouldn't do this condition. Okay, so should we change this? like this. We add answer and document ID of P1. Okay, and what else? Very good. Okay, so here we add P1, here we add P2, here we just add one of them because they are the same. They are the same, so we add one of them. So that will remove the duplicates. Okay, so that will take care of the duplicates. Is that it? Why not? Yes? Yes. So outside this loop, because we will get out of this loop when one of them has ended, right? But still there are remaining documents in that list that we didn't finish. So we'll have to have another loop and just add everything in that remaining part to the what? To the answer. To the answer. Okay.
Could you talk?
Let me get what Muhammad is saying. Yes, Muhammad.
Yeah, sorry to interrupt, but I was curious. How do we make sure we keep the fact that the lists will be sorted? Because
It is
by,
already sorted,
by
Muhammad.
design. No, but because we're adding essentially ad hoc, so like there is no guarantee that.
Oh,
for
no.
example,
When we stop, okay, so when we stop here, we know that the rest is sorted also. And we know that everything here is greater than that list.
Because essentially, if you go back to the code, like we're not caring, like whenever we're adding, like
No, but
if like for example here is 2, like we'll essentially add 1 and 2 and then like go back and add 2, no?
oh no, because we will add whenever we have a match. We will not change this. Whenever we have a match, we'll add it once, and we advance both. So we'll add whenever we have duplicates, we'll just add it once. We don't have it twice. Okay.
Like so. Yeah, I still don't understand how this would work.
So did you understand and?
Yeah.
Okay, so let's quickly do it as if we are doing or. Okay, now. Okay, so we'll start here. What should we do? We compare. There's no match. What should we do? We add 1. Okay, so let's assume here that this is the new list. Okay, for or. So now we add 1 to the answer, and then we advance 1. Now we have a match. What should we do? We add 2 just once, and then we advance both. Now we have 3 and 4. We add 3, the smallest, and we advance 3. Now we have 4 and 5. We add 4. You see how it is sorted now without duplicates, Muhammad?
Thank you. It seems that I misunderstood how AND worked in the first place. Thank you for correcting that.
Okay, no problem. Any other questions? Is it clear now? So you know how and or work, right? Okay, so you can get the rest, right? Okay. Right. Now there are more general merges. Okay, we talked about single operations, right? But remember, the Boolean expression can have multiple operations. So, and also there are other operations like not. So how can we do and not? Or not? Okay, so we'll leave that to you to think about. Also, what about an arbitrary Boolean expression? Okay, something like wink or drink and like or not ink. Okay, how would you do that? Yeah, it's modular now, right? So we'll do the operations with the specific order of the Boolean expressions. Okay, every operation will provide to us posting lists. So that will be an input to the next operation. So for example here, okay, let's say that or not is an operation. So we'll get 1 posting list out of this operation and 1 posting list out of this operation. Then what should we do? So we assume that we have an operation or not done, and we have or that is done also. Okay, so that will give us posting list here, and which is the answer set. Okay, answer set is kind of, it's like a posting list, and posting list here also. for or. Now what should we do? We do the AND between these two posting lists to get the final answer. I will leave that to you. Think about it. Okay? Maybe. Possibly. Supposedly. Yes? It is given to you. Yes, the number of documents, yes, the number of documents is given to you, and you can assume that if the number of documents is n, then the document IDs are from 1 to n. Okay, now let's go through a quick, of course it is a big topic, but we just go through it very simply now, which is query optimization. What do you mean by query optimization? Whoever, I think most of you took database courses before, right? Right? I assume. Right? No? Most of you at least, not maybe not all. What do you mean by query optimization in databases? Query optimization. Forget about databases. If I told you query optimization, what could be the meaning?
Essentially, we try to simplify the query to something that doesn't do any redundant checks.
Yes, so we want here to do some tricks maybe to evaluate the query or to optimize the processing of the query in terms of time. Okay? How we make it a bit more efficient. So for example, let's say that I want to do this query, like and wink and ring. Okay? This is a big query, right? We will not do it at once, right? We said that we need to have every operation, and then we combine these operations together. Okay? So here we have how many operations? We have 2 operations. So we can do, of course, AND is commutative, right? So we can say, we can do like and wink, and then the result of this will be an AND with the ring, right? So this is the first AND, and that's the second AND. We can do that, right? Okay. Or we can also do it in another order, right? We can do this first. Then we do it with this, right? Which order is better? First, will the answer set be different if we change it that order? They will not be different? What do you think? If we change the order of the operations here, will we get different answers? Okay, so the order will make a difference in terms of the answers? No, they shouldn't, right? Because the AND here, the order is the same. Whether you do the first AND or the second AND, the answers will be the same. Okay, so it's not about getting the correct answers here. It's not about you will get the correct answers, but it's about how to make it more efficient. Okay, so to do this, if we have AND of multiple terms like that, think with me. Which one you should do first? The 2 largest first. Okay, so I heard one answer to the 2 largest. Why is that? To get rid of them.
I'd say the smaller one.
Muhammad, just wait, there is an answer from here. But that's the worst case. That's the worst case. Okay? In optimization, you look for the average case, right? Not the worst case, because the worst case will not happen every time. Okay, the worst case is the size of both, right? The sum of the sizes of both. But in reality, you don't get to the end of every of both, right? You get to the end of one of them. Can I get an answer? Yes. Yes, please. Okay. Okay, so with the and we stop at some point. Okay. Okay, so I understand this stopping issue, but if I intersect a very short list with a very long list, what will be the size of the output? The shortest exactly, yani? The maximum size of it will be the shortest. So it will be probably less than the shortest. Okay? So if I take this and intersect it with the second or the next posting list, I will get even shorter, right? Because the complexity is the size of the length of the posting list. So whenever I can make the intermediate lists shorter, that will take less time. Did you get that point now? Okay. Type. If that's the case, Muhammad, you have still a question, or do you want to answer?
It's all right. As you alluded to, like that's all I wanted to point out.
Okay. Now, anyone can suggest an order here? Yes. Drink and like, which actually was not one of the orders that we mentioned even, right? We didn't. Okay, so drink and like first. Why? Because they are the shortest, and when we do the shortest, the resulting list or answer will be even shorter than them. Okay, so we'll do that. Then we do the end with the other one. Then the chance is higher that we don't go through very long lists. Okay, so that's a quick idea about query optimization. We'll start here with, say it again. The shortest of them, which is like and drink and like. Which ones are the shortest here? Which one? We cannot start with one only. And has two. So the shortest two here are drink and like. Right? Why it's better? But we cannot generalize that because you might have and with 5 or.
I'm not sure which one.
So these are heuristic, by the way, heuristics. This is the heuristic. And this is not guaranteed to get us always better than other orders. Okay, it's just a heuristic that we start with the shortest because over time we need to get shorter intermediate posting lists. Okay. Yes. Where is the question? Think about that. So we talked about and here, right? So what if we have or? Will it make a difference or not? Think about it. Okay. Now, any question about what we covered so far in Boolean retrieval? Is everything clear? Do you know now what is Boolean retrieval? Does Google do actual Boolean retrieval? We know the answer.
If you choose to use it.
Huh? Maybe Internet Explorer. You have a very bad But Internet Explorer, by the way, is not a search engine. It's a browser. Okay, but it seems like you have very bad experience with so it's. But Boolean retrieval is bad. Is that bad? Yeah. It's not. We said that it's used, right? It is used. Okay.
We can use it even in Google.
We can
To
use
limit
it in
by
Google,
site.
yes. Where
To
Muhammad,
limit-
just 1 second. Where Muhammad? How did you know that we can use it in Google?
I used to use it all the time. Like if you want to exclude specific sites from your search result or include some. Similarly, like excluding specific keywords.
Exactly. I told you last time, look at the advanced options, right? These are the advanced options. Okay. طيب. Any other questions? So Boolean retrieval is good or bad? It depends on the task, yes. But it will be good that if the system allows you to do that if you need, which Google is doing. Okay, now let's talk about a type of queries called proximity queries. So what is that? Now, let's say that I have a document and if two words in that document are close to each other in terms of position in the document, okay? Do you think this is an indication that they are related more or less than if these two documents are very far from each other in the document? Yeah, let's say that we have two words, Qatar and university, okay? And we have two documents. One document, Qatar and university are very close to each other in that document. They appeared closely, nearby. And in the other, one appeared in the beginning of the document and the other appeared in the end of the document. Let's say that just once here, once here. So if I type the query Qatar University or Qatar and University, do you think that the first document is more relevant than the second document or not? Yes, right? So proximity here has generally corresponds to relevance to some extent. Okay? So we would like to see the document that has the words nearby, probably more than the documents that have these words very far. So far with Boolean retrieval, can we do that? Why we cannot do that? Yes, because Yes, we don't keep track of the order. Once we do this pre-processing, these two documents will be the same in terms of Boolean queries, right? Because we don't know where Qatar appeared and where university appeared. It's this story. No. Okay. Right. This is an operator that actually is used. It's called the near operator. Okay. So I want to find. So this is related to Boolean. We'll get to it. We'll get to that relation. But this is a different type of operations. We saw and, or, not, right? You can think of it as another operation here, which is near. Okay, and near has a parameter, which is the number of words that we allow to appear in between these words. Okay. So, for example, a query, find gates near 3 Microsoft. What does that mean? It means find me documents, not only that have both Gates and Microsoft, but they have Gates and Microsoft within 3 words of each other. Okay, so that's more restrictive, more specific than just Gates and Microsoft, right? But you can think of it as an operation now that can be added to the set of operations we talked about before, because that operation will give us also a list of documents that will match that operation. Although it's not, we are not used to it in Boolean algebra, but it's also Boolean, because the document will match or not, right? So here's an example implementation for it, or meaning for it. So near n, return a document D if all query arguments, which is Gates and Microsoft here, occur in D in order. So that's a specific implementation for it, okay? appear in order with no more than n minus 1 terms separating two adjacent terms. So what does that mean? With an example, if I said A near to B, so the documents that will match this operation or this query will have A and B adjacent to each other, or A and B with only one term in between, but not two. And something like AXYB will not match or should not match. Okay? AXB will match, AB will match. Okay? Is that clear?
Just a
Yes.
bit technical question, Doctor.
Yes.
Is this a DOS format?
Is that what?
Is this a DOS format like near -2?
DOS
'Cause
format?
I don't recognize it as bash.
No, it's some of the search engines have this in their query language.
Yeah, because as you mentioned before, like they usually bring up like examples from like bash or Unix, so this looked like more like
No, this
DOS commands.
this is. I'm not sure if there is a Unix command that is similar to that, but I know that some search engines actually implement something like this, and it is useful actually. Okay, now how can we support this using Boolean retrieval? Can we use what we studied so far in the lecture to support doing something like this? Not to sort. Okay, but still, do we have the information that we need? What kind of information we need here that should be stored somewhere to support? Oh, but how many? If we do that, then we need to have for every pair of words the number of words between them. That's not efficient. What does that number represent? The position. Very good. So it seems like what is missing to support this operation is the positions. We have to keep track of the positions. Otherwise, we will not be able to match documents with that operation. And how can I know that A and B appeared in the document not far more than 3 or 2? With what we had so far in the index, we're not able to do that. Because in the index now we keep it as bag of words. We don't keep the order. We don't know anything about the relative order of words. So the positions are needed here. Yes, of course. Yes, of course. So since you said that, where should we store such information? Can you raise your hand, please, before you answer? Yes. What do we call it? Yes. In the posting list. Where exactly in the posting list? Yani, every posting corresponds to what? Okay, but we need to generalize that the term can appear multiple times in the document, right? So it's not just one position, it's list of positions. So we'll have to store that in, yes. Oh, you had a question, not an answer. So let me answer this and then we'll take your question. So we'll have to store this where? In the posting, in each posting. In each posting. Remember, each posting is, and if we have this, this is a posting list. Exactly. It has inside it. So we have, for example, we have the word gates. Okay, gates, and gates points to this posting list, right? So far we had just the document ID here. We had the 3, 14, 22, 101. These are the document IDs in which gates appeared, right? Now I want to store also the positions in each document. So here somewhere we should have list of what? Of positions of what? Of gates in what? In the document number 3. Okay, and we have to have this for every document. Okay, so this posting is part of this, sorry, not posting. This position list is part of the posting. Okay, is that clear? Sorry? It's position list. Yeah. Position list. Okay, so that's the solution, and we call this type of index positional index. Logical, right? Huh? Exactly. It's like, no, it's not the dictionary. It is. It's like what? Okay, the dictionary is the entire book, right? Okay. Where is the dictionary here? I don't see it. But I thought that you were talking about the actual dictionary. You know the actual dictionary, the book that we use? What does it say for each word? It's inside the page here. So let me explain this. Okay, so what is this as a whole? This is one posting. This is the posting that corresponds likes. Sorry, this is not the one posting. This is the posting lists. Okay, so this is postings list for likes. Okay, what is this? This is the DF, document frequency. Okay, and each of these is posting. Okay, wait, it's just one posting. The first number here is the document ID, and the rest of numbers, because you have column here, right? The rest of numbers is the positions. Okay, so all of these the positions. Okay, is it clear now? So inside each posting, there are, at least for now, 2 things. Later you will see that we can add more things. We have the document ID and we have the list of positions. Oh, of course, man. Yeah. We just see part of it. Yeah, we just see part of it. Yes. We should have 9,347. If you want to do, then you can. You are welcome to do it. No, 5. It's still the position is. Yes, it shouldn't be closed. Yes. No, but this is a. Yeah. Actually, this is closing this, by the way. Oh, that's why the ellipsis here is for everything. It's correct. The ellipsis here is for everything. Anything else. Implicitly, yes. Okay. Type. Any questions about that? Type. What is the biggest problem here? We can do that, right? We can do that. Now we can modify the algorithm that we saw earlier to keep track of the positions, right? We can do that. Or not? We can. Now just keep track of the positions when we build the first list. Okay, and then we aggregate them. But what is the biggest problem with that? The space. Why is that a problem? Imagine what is the additional space that we have to add. What is the size of that space? Which is which is the size, the actual size of the collection. All the terms in all documents, right? That's the total position list, which is everything. So that's huge. That's like the collection itself. Okay, so that's the biggest problem, the index size. The index size will, of course, increase substantially. Usually, it is doubling the size of the index. When you add the positions, roughly you are doubling the size of the index. But of course, there are compression techniques. Unfortunately, we will not have time to cover compression here in this course, but there is, of course, nice work in compression of the index. Although we have compression, but still with very large collections like the web collections, it is huge to keep track of this. But now with the low cost of disks and more power of processing, many search engines use actual position indexes. Okay? And I think if you think about it, if you remember what kind of results you get from search engines, you will see that the documents that have the words close to each other are usually much higher in the result list than the documents that have the words far from each other, which means that there is a kind of proximity measures that are used in retrieving the results. Okay. There is another type of queries called phrase queries that is related to proximity queries, but it's more specific, and I think we all use it. If I want Qatar University as a phrase, Qatar followed by university. It's not near, it's immediately followed by university. Okay, this
distance should be 0.
Sorry? The what?
Shouldn't the distance be 0 then?
Look at the definition, exact definition. It's not exactly 0, but you can. Yeah. So one way is use near operation with 1. With 1 we'll do it based on the definition that we had before, because we allowed n-1 words in between. You want n-1 to be 0, so n has to be 1. So you can do that. You can do that using just the near operation. But will that be efficient? Let's get back one step here before we switch to the phrase queries. We didn't talk about that, by the way. How will we do the near operation actually using the position index? Now we said that we need position index, right? We need to store the positions. Now let's assume that we've stored the positions. How will we match this operation? If I said near 3, what would we do? Raise your hand, please. Yes. Yeah, let's say that. Yeah. Huh? Say it again, please. Subtract. What do you mean by subtract? Intersect. We do and, right? It's like and here, but it's more restrictive than and. صح? No. So when I say near, implicitly this is an and operation, right? Because I need both words to appear in the same document. So we'll have to start with the intersection algorithm that but it's not enough, right? We'll have to do something with the positions. What do you mean by minus then? So we have to compare the positions. But before we compare the position, we have to get the matching. We have to get the intersection first. So let's say that we got a match. Now we have this document in this merge algorithm. When we get a match, we will get the positions for these documents, right? Because these are position of the 2 terms. Right? Now we have 2 positions. This we have to compare them somehow to see if that document matches the near parameter or not. It matches and, we know that. But we need to, because there's one more condition, which is the near condition. So we have to check it given the two lists of positions. Okay. Okay. Yeah, think about it. Many things can be done, right? Okay. Well, unfortunately, we will not be able to work out together every single detail, but at least we need to cover the basics, and then, of course, there are many things that can be done. Okay, so here we have to answer two questions. I intended to leave them to you, but actually you answered the first question. How can we support it using position index? I think we discussed it already. There is another type of index in the readings called byword index. Okay, so read it and think whether this would be more efficient than positional indexes and why. Okay, we'll leave that to you. Okay, now one more operation. Again, if you want to leave at any time, please do. One more operation called syn, which indicates synonyms. So what do we mean by synonyms? Words that have the same meaning. Okay, like here, begin, start, fast, quick. Now, what if the document has begin and the query has start? Should we match them or not? What if the document has fast and the query has quick? Should we match them or not? Okay. Of course, it will be easier if the search engine itself does it, but sometimes it's not easy to really know the synonyms. And sometimes you yourself know that that you might find this in the collection that you are working on, so you want to explicitly mention that to the search engine. So we'll use something like that. Some search engines actually allow that, to use the operator synonym. Okay, and you give two words, something like this. Fast, sorry? Yes, we'll get to that. Okay, so we'll write it like this: fast, or this is one way of writing it. Fast, same, quick, which means please consider fast like quick to the search engine.
Doctor?
Yes. Yes, Muhammad.
It's not to bother you, but I'm curious, how is this any different than just using the OR operation?
So you think it is exactly OR operation, right?
I mean, from the looks of it, yeah.
Okay, type. One way of dealing with it is to think of it as OR. Okay? And that's it. But do you think this is is it exactly the same like OR? Think of it. Synonym, why not?
Some words that came together, if we change one of the synonym, maybe not what is meaning. So we'll change somehow the context. The same.
It is very similar to OR, but there is one in terms of implementation. Yes. No. We are not talking about meaning. This is maybe what the user is, but the actual thing here is we want to say that whenever you see fast, consider it as quick. Okay, consider it as quick. So what should we do if for that case? Yes. If that word type, if It's another word like, but both, but combines both. We will not compare it. Okay, طيب, and I agree with many of you who think that it is like very like all, okay, but with only one difference. Yes. We can, okay, but now fast is gone. Right? If you change heavy fast with quick, fast is gone. And you will not be able to match it. And the opposite also is not good, right? So the idea here is that with that query, when we get something like this in the query, we get, okay, so this is the answer to this question. We get the we get the posting lists, and the only bad difference between this and all, we need to merge the positions. We need to merge the positions so that we can support proximity queries for both. Did you get that?
I mean, I thought that was already implicit when we use or with the positions, no?
But or by itself doesn't care about the positions, Muhammad.
Oh, I see. So this is more holistic then.
Yes, but later you might say, give me, give me, the query might be like this, okay? Fast, sin, quick, and, not and, sorry. Near مثلا 5 diet. I want fast diet. Okay, if there's something like that, or quick. Okay, now it's not fast diet or not quick diet. Okay, it's any of them. So any document that has fast near diet or quick near diet should be matched. So the idea here is that we do something like all, but we only need to merge the positions. Okay, so that will be the difference. Yes. The positions only. With all, we don't care about the positions. In all, doing all, we don't care about the positions. Because any document will be a match. But with synonyms, we need to keep the position because it doesn't matter which one appeared, but it matters where it appeared. Any one of them. That's what we will do.
Doctor?
That's what we will do with all the positions. If there is a match. Okay, let me give you I think a clear example. Maybe that was not very clear. If a document this will appear, this issue will appear if a document has both. Okay, so if a document has quick and also has fast, some positions in the document has quick and some position has fast. Okay, and I don't know which one should be nearby diet. I don't care which one. Maybe in the actual document there is a fast diet, but there is no quick diet. Okay, and in my query I don't know which one. Anyone, I want anyone. Okay, so I want to treat these two as if they are just one word, call it, or one term, call it like quick, fast. A new term that is called quick, fast. Now I can replace any occurrence of, logically, we don't do that physically. Logically, we can replace any occurrence of quick by quick, fast, and any occurrence of fast by quick fast. It's like that. It has this effect. Yes,
So
Muhammad?
doctor, just to be clear, does that mean like if I try to say fast or quick near 5 diet
Yes.
will be incorrect syntactically, right?
Yes, kind of. Yes, I think yes. It would be incorrect.
All right, thank you very much.
Yes. You can. You can. I think it will be the same. Yeah. But this is easier to write. Yeah. And also, I think in terms of performing the query, instead of doing 3 operations, here it's just 2. Yeah, I think this will be more efficient. But the result will be the same. Yes. Should we stop here? Yes, we have to apply sin first to merge the positions, and then we apply near. No, the documents, of course, the documents, yes. Should we go through this quickly? Okay, 5 minutes. 5 minutes, okay? Stop me after 5 minutes, okay? Okay, so fields and zones. What do you mean by that? Sometimes the documents have metadata, like the author of the document, okay? Or when was it published, right? Or the title of the document. How can we deal with that? What if I want to match to get the documents that have Shakespeare in the title and country in the body of the story? How can we do that if we will not deal with this in a special way? We'll not be able to do that, right? So we'll have to distinguish what we call the fields. We might have author, we might have title, date of publication, language, format. All of these are metadata that comes with the document. So if I want to find documents authored by William Shakespeare in the year 1601 containing these words, then I have to keep track of where, not only the positions of the words, but which field it appeared in. Yeah, so these are 2 fields. We have to distinguish between Shakespeare appearing in the header or the title and Shakespeare appearing in the body of the play. Okay? So each of one of these is called the field. So year equals 1601 is an example of a field. Author last name is a field, and so on. Now, there are 2 types of fields. Okay? I know that might be confusing a bit in terms of the terminology. All of them are called fields, but some of them are called fields. Okay, so let's distinguish between 2 things. Okay, when we say field, we mean fields that have specific values. The others that have text are called zones. Okay. Is that clear? So authors are fields, are not zones, because they don't have free text. Okay? So whenever you have free text, then this is a zone. Like the title. Title has free text, right? So it's a zone. Author is a field. Okay? So for fields, we have a term for each field. We have an entry in the dictionary for each value. Sorry. Okay, so that we have postings for each field value. يعني no. For each field value. يعني let's say that the year of publication is a field, right? Because it has the years. But over the entire list of entire documents in the collection, we have a specific set of years. There will be a posting for each, posting list for each year. Like there is a posting list for each term, but there are no terms here. That's the issue here. Okay, so some of the fields will not be free text. There will be years, there will be names. Okay, so we should not, for example, we should not say we should not tokenize years, right? It's just numbers. We should keep the numbers, even if in pre-processing we might get rid of numbers, as we will see later, inshallah. But here we should not, because these numbers are the values for the field. Okay, so we'll keep it as the terms here will be the numbers in case of the year field. Okay, but zones will have free text. Like what? Like the title, like the body of the document. Okay. Yes. Exactly. Yes. Thank you. Yes, it has special structure. Okay. It is a specific type. It's not free text. So anything that's not free text is called a field. Anything that's free text is called zone. Okay. Right. What? Yes, it can be enumerated. Yes, exactly. Why do we distinguish? Why do we distinguish between these two? Because for zones, we will deal with them as we dealt with earlier, right? We will tokenize, we will do the pre-processing. But for the fields, we should not, of course, do any pre-processing. We just take the values as they are. That's exactly why we distinguish between these. Okay? Saying that, so a zone is a region of document that contains an arbitrary amount of text, free text like title, abstract, references, and so on. Now we will build inverted indexes on zones. So any zone, any part of the document that is zone, that has free text, we build an inverted index for it. Right? So you can think of it as separate indexes. One for title, one for body, one for abstract, and so on. Logically, they might be separate, but physically, they might be in the same data structure as you will see in that last slide. So here's an example of how the index will be in that case. Okay, so you will see that the terms now have an indication of where they appeared. So William.abstract, this is the term when William appears in the abstract. So that means that William appeared in the abstract of document number 11 and document number 121 and so on. Okay, William appeared in the title of these documents. Title, so there is William.title here. That means this is about the zone title. William as an author appeared in 2, 3, 5, and 8. Okay, so this encodes the zones in the dictionary. Remember, this is the dictionary, right? So that's encoding the zones in the dictionary. There is another way of doing it, which is encoding it in the postings. So here's how it will look like if we encode the zones in the postings. So it will be William, as we did before, but now we will, for every document, we will say where it appeared. So instead of having 2 here only, we have to say 2 and author, 2 and title. Of course, we don't have to repeat these 2. We can say just 2 author and title and so on. This is just for presentation issue. Okay? And here it appeared in author, here appeared in title, here appeared in author, and so on. So these are 2 examples of how we can deal with fields and zones in an inverted index.
Right. Thank you very much, Doctor. See you next week.
Okay, thank you.
If there's any assignments or anything,
Sorry?
just before I disconnect, is there any information or assignments?
No, we are
that's all?
done. We are done. Thank you. Sorry for
All right,
giving
then.
you that late.
Yeah, I apologize just because my brain started to shut it down, so I honestly had to let you know before I
Oh,
fall
no
asleep.
problem, no problem.
But again, thank you for the session,
You're
doctor.
welcome. Any questions?
مع السلامة.
Everything is clear, or you want to leave? Or both?
Thank you, doctor. Thank you.
Both? I hope so. Okay. We just went late today because of this setup. Takes time in the beginning. Inshallah, we'll try to stop on time for next lecture. Okay. See you inshallah next week.